Hi everyone and welcome to a new video about noise analysis in op-amp circuits. This is our example number 8. In this example we will discuss a two-stage amplifier, and of course we'll look at the calculations and also the spice simulations to verify our calculations. So let's look at the example. We have the following circuit given. We have the two operational amplifiers, OPA 209, OPA 209. We have the resistors R1, R2 with the values here shown here. R1 is 3 kilo ohms and R2 is 150 kilo ohms. R3 and R4, which is then 2 kilo ohms and 10 kilo ohms. We see actually two inverting amplifiers in cascades. So what we want is the input referred RMS noise voltage and also the output referred RMS noise voltage for this circuit. We already discussed in the previous examples the single stage amplifiers where we have analyzed the noise performance. In this case we see for the first time the two-stage amplifier, and we will then discuss what the performance is of this two-stage amplifier. So let's look at our solutions. Of course we start with the op-amp specification. In a specific case we have now two same op-amps, OPA 209, so we can just focus on one of these. So this is the plot what you get from the datasheet of this OPA 209. This is the plot of the input noise voltage spectral density on the left side, and this is the input noise current spectral density on the right side. And we have also some parameters from the datasheet which will be used in our noise analysis. Now let's start with the first one. This is the DC open loop voltage gain, which is given by this symbol. It is 132 dBs, and that is also shown here. The symbol is here and also the description. We have the gain bandwidth product, which is 80 megahertz, very important parameter, which is shown here, the gain bandwidth product and the frequency response part. And we have also the noise specifications, the broadband noise voltage spectral density given by this symbol. It's 2.20 nanovolts per root hertz. That is shown here with its own specific unit. It's the noise density. But you can also see that in the plot on the left side here, that this part is frequency independent. We have also the part which is frequency dependent that will be discussed shortly. Now we have also broadband noise current, similar to the broadband noise voltage spectral density, given by this symbol. It has a value of 500 femtoamps per root hertz. That is shown here also in the table, the value and also the unit, but it's also shown in the graph on the right side here. So you can see 0.5 picoamps per root hertz, which is then 500 femtoamps per root hertz. Now going now to this actually this region which is then frequency dependent, which is then called 1 over F noise voltage spectral density for this part, and it is defined in this case for a frequency, specific frequency, in this case 0.1 hertz. That's given by this symbol. It has a value of 20 nanovolts per root hertz. That is shown here, 0.1, and it has a value of 20 nanovolts per root hertz. In a similar case for the 1 over F noise current density, again at the same frequency given by this symbol, it has a value of 3.75 picoamps per root hertz. It doesn't matter actually which frequency you take. If it is in this region, in this 1 over F region, that will be fine. So these are the parameters we will use, the op-amp specification for our noise analysis. So let's look at the next step, which is then the circuit performance. Now, since we have now a two-stage amplifier, we will of course look at each stage separately. Now again, we need to look at the gain. So we have the closed loop gain and also the open loop gain, of course, but in this case we have a closed loop system, so it is closed loop signal gain and a closed loop noise gain. For the noise analysis we will use this one, and for the performance in the frequency, of course we need to look at the bandwidth. Of course we have the signal bandwidth and also the noise bandwidth, so we need to make a difference between these two. Now for the first stage we can see it is a inverting amplifier. The signal gain is just minus R2 over R1, very familiar formula. If you don't substitute the values, you will get minus 50. The noise gain is always defined as a source which is in the non-inverting input. You then set the signal source off, so you disable the signal source. That will be a short here, and you will look at actually from this non-inverting input, that will now give you the non-inverting amplifier formula, which is then 1 plus R2 over R1. That's shown in. If you now again substitute the values, you will get 51. So the noise gain is a little bit larger in magnitude than the signal gain. Now that's for the first stage. Now also look at the signal bandwidth for the first stage, which is just gain bandwidth product over the noise gain. Gain bandwidth product from the OPA 209 was given in the datasheet. 18 megahertz over the noise gain will be 353 kilohertz. That will be the signal bandwidth of this one, the first stage. Now the second stage, in a similar form, you again use the signal gain formula, actually the inverting amplifier from this node to the output, which is then minus R4 over R3, given by this formula. Again, we have minus 1000 over 2000 will give you minus 5. Okay, that was the signal gain. The noise gain again, you will of course look at from the non-inverting input, that will give you 1 plus R4 over R3. Again, the non-inverting amplifier formula, you will now have 6. So in magnitude, noise gain of the second stage is then a little bit larger than the signal gain. Now, if you now look at the signal bandwidth of this second stage, that will be again the gain bandwidth product of this op-amp divided by its noise gain. That will be the 80 megahertz over 6. That will be 3 megahertz. What you see is these two stages have definitely a different signal bandwidth. So that will be of course now determine your actual bandwidth of the complete circuit. Now, the signal bandwidth of the first stage is much smaller than the signal bandwidth of the second stage. So if you set this in megahertz, it will be 0.353 megahertz. It will be approximately 10 times smaller than that one, at least 8 times. Now that means actually this is the much smaller. In that case, the two stages are also in cascade. Now for these two conditions, since the first stage has a much smaller signal bandwidth than the second stage, and it has in cascade, then the closed-up signal bandwidth of the second stage is limited actually by the closed-up signal bandwidth of the first stage. So that is a condition what we have here. And that means actually the signal bandwidth of the second stage is also approximately actually equal to the signal bandwidth of the first stage. So you can say this signal bandwidth, which is then just independent calculated for the second stage, will not occur actually for the complete circuit. Now for the closed-loop signal bandwidth, just the total signal bandwidth for the complete circuit will be then determined by the stage with the smallest signal bandwidth. That means actually the following, that the signal bandwidth for the complete circuit will be then the signal bandwidth of the lowest signal bandwidth, that will be then 353 kilohertz. This will be then again used later on in our noise calculations. So assuming a first order circuit, which is not completely in the complete frequency range, but in the vicinity of our noise calculations, and also using a break-wall conversion factor, which is then for the first order system pi over 2, which is this symbol k sub n, I can then calculate the closed loop noise bandwidth for this complete circuit, which is then given by the noise bandwidth. This is then the conversion factor times the signal bandwidth for the complete circuit. Now, if I now do the math, just very straightforward, pi over 2 times that 353 kilohertz, I will have 554 kilohertz. That is now the actual noise bandwidth, of course with the approximation we have made, just assuming the complete circuit is the first order. This will be our noise bandwidth, which will be used for all calculations for each stage. So for the first and the second stage, we will use noise bandwidth of 544 kilohertz. Okay, that's for this circuit performance. So let's then look at the noise in total form. We have of course the noise from the first stage. The important thing we need to consider here is that noise from the first stage will be multiplied by the signal gain of the second stage. So if you have a noise at the output of this first stage, it will be multiplied by the signal gain of the second stage. This is a very important note. But the noise of the second stage, so it is own noise, we will multiply the noise gain of the second stage. So this is actually a very important point here to consider. So if you now look in general, the noise sources will be multiplied by the noise gain of the stage it is connected to, which is actually shown here in the first one. And the noise source will be multiplied by the signal gain of the subsequent stages. So actually what I meant by this form. So noise source will be multiplied by the signal gain of the subsequent stages. Now this general form is very important. We need to consider this. So if I now move from this to this, which is of course the model where we see the current and the noise voltage sources, and also the current and the noise voltage sources actually for each op-amp, and also of course the R1, R2, R3 and R4, then we can use superposition to calculate the actual noise performance. That the calculation using the superposition is actually carried out using the following step. First, calculate the output noise voltage of the first stage, considering this as a noise-free amplifier. Then calculate the output noise voltage of the second stage only, and then combine those two results using the root sum of squares. This will be of course clarified when we do the calculations in numerical form. So let's also make some notes. This is very important. Noise from the first stage amplifier will be slightly reduced by the bandwidth limits of the second stage. So because there is a pole due to this first stage, there's a pole due to this second stage, because the pole frequency of this one was 353 kilohertz and this was 3 megahertz. Of course they will interact and they will create of course some pole shifting. So it is not exactly that the cutoff frequency of this one will be 353. That will be slightly less. Now this can slightly also reduce the total noise bandwidth. It will of course also result in a little bit less output noise. So we will see that also in the simulations. Now the rule of thumb what we use is when several amplifiers are cascaded, the noise bandwidth is approximately equal to the lowest noise bandwidth. However, some of the higher bandwidth amplifiers will still roll some noise. So that will be of course the case. So it is in general true that if you have a stage which is then has a lowest noise bandwidth, this will then dominate. And most of the time that will be the case. So if you now look at the first stage, again using the description here, so the output noise voltage in RMS for the first stage only then will be then given by this, so the noise gain of the 1 times the signal gain of the second stage times the input referred RMS noise voltage of the first stage. So this will then produce at the output this noise voltage. Now the second stage on its own will do that in this form, so it will then be the input referred RMS noise voltage of the second stage will be at this node times the noise gain of that stage, and that will be of course also output noise voltage at the output. Now those two will be combined. Now let's then look at the first stage first. Now the input referred RMS noise voltage, this one is composed of 3 parts, and those are the input referred RMS noise voltage due to the internal op-amp noise voltage source, which is then due to this one, and we have also the input RMS noise voltage due to this noise current source of the op-amp, and we have of course the input noise voltage due to the resistors of the first stage. Now if you combine those, just specific looking for the first stage, you will have this expression. You can see it is just given for first stage. Now if I now calculate this for the first stage, I can first start with the first part of this input referred RMS noise voltage for the input stage is the input referred RMS noise voltage due to that op-amp noise voltage source. Now that is on its own also composed of 2 parts. So we have the broadband noise voltage, spectral dense noise voltage, and also the 1/f noise voltage. Now those are again combined using the root sum of squares in this expression. Now the broadband noise voltage in RMS is given by this expression, and for that we need of course the input referred RMS noise voltage spectral density from the op-amp data sheet and also the noise bandwidth for our first stage. Now from the datasheet we see it is 2.20 nanovolts per root hertz, and also the noise bandwidth it was 544 kilohertz. Now if you do the math, you will get 1.64 microvolts RMS. Now for the 1/f noise voltage, this expression will be used, and for that we need the upper cutoff frequency, which is then the closed loop noise bandwidth. We have a selected frequency, which is also the frequency we use for the normalized 1/f noise voltage. For that we use the datasheet, and this selected frequency can be anything in that 1/f noise region, but in this case we is 0.1 hertz. So if I look again to the op-amp specifications, we see it is then for this frequency it is 20 nanovolts per root hertz, actually what we have for this one. And if you now calculate this, you can see for the calculation here it is 6.0 33 approximately nanovolts RMS. Now if I now substitute the values in this expression for the 1/f noise voltage, that will give me 25 nanovolts RMS approximately, and in microvolts it is 0.0249 microvolts RMS. Now we need to combine this, of course, the broadband part and also the 1/f noise part. Then we have the following expression, of course, using the root sum of squares, and you will get 1.64 microvolts RMS. In this case, you see again the broadband noise voltage for the first stage is dominant. Now looking at now the next part, which is the input referred RMS noise voltage due to that internal op-amp noise current source, which is this one for the first stage. And again, it is calculated using the noise bandwidth and also the rest of the parameters, but in this case, since we have a current source, we need to have the equivalent resistance seen by this noise current source and also the noise current source of this value in RMS value. But the equivalent resistance in the first stage is the resistance seen by this noise current source, and we use the Ohm's law to calculate the op-amp input referred RMS noise voltage for the first stage. So it is the current times the equivalent resistance. So this noise current source in RMS is also composed of two parts. We have seen the 1/f noise region and also the broadband region, and that is again calculated using the root sum of squares using this formula, the total. So the broadband noise current given by this expression, again you take this from the datasheet, which is shown here, 500 femtoamps per root hertz. This is of course your noise bandwidth. If you now substitute the value, we will get 372 picoamps RMS. Now for the 1/f noise current, you have a similar expression as we did for the 1/f noise voltage. Again, the upper cutoff frequency as the noise bandwidth, the lower frequency as our normalized 1/f noise value for this specific value using the datasheet, and also we will here use 0.1 Hertz as the F sub L1, and that is shown here, 3.75 picoamps. So if I now use that and then calculate the I sub F norm 1, I will have 1.186 picoamps RMS. Substitute that in this expression and then use the noise bandwidth here and also the 0.1 Hertz here. I will have this value of 4.67 picoamps RMS. So we have the broadband part and also the 1/f noise part. So then we can calculate the total value of this one using this formula, which is then this, and that will be result in 372 picoamps RMS. Again, you see here the broadband noise current will dominate. Now the equivalent resistance, of course, for the first stage is just looking from this source is the R1 and R2 in parallel, because this will be disabled. This is also disabled, so it goes to ground. So for the non-inverting input, you don't have any resistance. For the inverting input, you will have R1 in parallel with R2. That is this, and it will be 2,941 ohms approximately. Now we have now the necessary elements. Now using Ohm's law, as we did also, as we discussed this here, just substitute the values, you will get 1.10 microvolts RMS for this input referred RMS noise voltage due to that noise current sort of op-amp. So we have the second one actually for this first stage. Now the third one, which is just the contribution of these two resistors, that is actually calculated using the white noise or the terminal noise formula for the resistors. Now the terminal noise or terminal RMS noise for the resistors is given by this expression, square root of the 4kT R, which is the specific resistance we're talking about, and also noise bandwidth. So the K is the Boltzmann's constant, which is this value. T is temperature in kelvins, and for room temperature operation, let's say 27 degrees, that will be a round number of 300 kelvins. So R is the equivalent resistance in ohms seen at the node, and the noise bandwidth is then given in hertz. So for this circuit, we have equivalent resistance of 2,941 ohms, and our noise bandwidth was calculated for 544 kilohertz. Now, then we have, using this formula, this expression, we have then 4kT, then specific for this resistor and also specific for this bandwidth. Then we have actually just calculating the values, we will have 5.20 microvolts RMS just due to the resistors. Now we can collect the necessary elements. We have now the third part, which is due to the resistors for the input stage. We can calculate the input referred RMS noise voltage due to that first stage. Now that can be done also using the root sum of squares, again using this expression. We already had that contribution to that noise voltage of the op-amp. This was the result. This was the result for the due to that noise current source of the op-amp, and this was the result just calculated for the resistors. Now if you combine these using this formula, then you will have this expression. Just substitute the values in it, and then you will get 5.56 microvolts RMS. You can see this is very close to that actually value for the thermal noise voltage of the resistors. So in this case, the resistors, actually the thermal noise of the resistors, will dominate again. Now the total output referred RMS noise voltage due to that first stage, of course, and then of course considering the second stage as noiseless, so noise free, then we have the following requirements. The closed loop noise gain of the first stage was 51. The closed loop signal gain of the second stage, because we consider this as noise free, then this is then 5. Of course in magnitude it was -5, we just take the magnitude. And we have the input referred RMS noise voltage for the second stage. We just calculate 5.56 microwatt RMS. Now we can then use the formula we already discussed for the output referred RMS noise voltage due to that first stage only, considering the second stage as noise free. That is then the expression. This must be of course the signal gain of the second stage. This is an error here. So we have then the Now we have collected all the necessary parameters for our output referred RMS noise voltage. The formula we already calculated and discussed actually. This is then the noise gain of the first stage, this is the signal gain of the second stage, and it is the input referred noise voltage RMS of the first stage. Now substitute the values, you will have 51 times 5 times that 5.56 microwatt RMS, and then you will have 1.42 millivolts RMS for the due to that first stage only. So this stage will contribute at the output, complete output, this much noise voltage. Okay, that's for the first stage. Again, in the summary, we have this output noise voltage due to that first stage. Now, let's look at the second stage. In a similar form actually, again, input referred RMS noise voltage, which is composed of 3 parts. I will go a little bit faster in this case. We have the internal op-amp noise voltage source, internal op-amp noise current source, and also the resistors for this second stage. Those will each then contribute noise, so you will add them up using this formula. Again, you will now calculate each of these using, of course, just considering one of them at a time. So if you look at this input referred RMS noise voltage, due to that input internal op-amp noise current source, that will be then given by, of course, the broadband and also the 1/f noise parts, or the broadband and also the 1/f noise parts. So that's actually this one and also that one. So if you now combine those together, you will have, of course, again the expression which will then calculate the total input referred RMS noise voltage due to this sort of the second stage. Again, using root sum of squares. So the broadband noise voltage, again, very similar calculation, but for this stage, remember, we use, of course, the noise bandwidth of the complete circuit, which will be determined by the first stage. So the noise bandwidth of the second stage will be equal to the noise bandwidth of the first stage, will be 554 kilohertz. So then we'll have this expression, again, using this from the datasheet. We see actually from our op-amp datasheet, which is actually shown here. So we have now the E sub BB, E sub MBB, which is then, of course, the broadband noise voltage spectral density. Substitute values, in this case, you will have 1.64 microvolts RMS. Again, it is exactly the same result as for the first stage. Of course, the next part is the 1/f noise. This again, there is a similar formula. You just substitute the values. Again, for the upper cutoff frequency, just the noise bandwidth of the first one, of course, because that is what we need. And then the selected frequency, and then using this formula for calculating the normalized voltage. Again, I will go a little bit faster because I have done this in great detail in the first stage. So we will have then the normalized value, and then using this we can then calculate the 1/f noise voltage in RMS. Again, this is all same for the first and the second stage because the op-amp is exactly equal to each other. So then we have the following expression, and we do the math, we will get again 1.64 microvolts RMS, and again this is dominating. Okay, now let's move again to the internal then op-amp noise current source, and that will of course also produce the noise voltage at the input. Now for the specific case for the second stage, again that will be then of course calculated using the equivalent resistance seen by the source for the second stage, and also the noise current source of that op-amp. So we have then of course the equivalent resistance seen by the noise current source of the op-amp. That is of course this one. We need to calculate that of course in the RMS, and of course using the Ohm's law we can calculate what the input contribution is of that noise current source. And that is on its own part also composed of two parts, which is the broadband noise current, also the 1/f noise current. That will be of course calculated also using the root sum of squares, which is then given by this expression. So the broadband noise current, and again in a similar form, we take from the datasheet the broadband noise current spectral density and also the noise bandwidth for the second stage, which is of course equal to the first stage because the noise band was limited by the first stage, which was of course much smaller than the second stage. If you just substitute the values, we will get 3.72 picoamps. It's exact same as the first stage, but the differences of course will be shortly because the equivalent resistance will be different. So again, the 1/f noise current in a similar form, just take the values for the upper cutoff frequency, noise bandwidth of the second stage. This is a selected frequency to calculate this normalized current value, and again 0.1 Hertz. I will go faster of course because this was done in great detail in the first stage. You will have then approximately 19 picoamps RMS. If you now calculate this value for the 1/f noise current in RMS, you will get 4.67 picoamps. Now we will now have the total effective RMS noise current value. We'll again calculate using this formula, and then you have then 372 picoamps RMS. Again, in this case, the broadband noise current is dominating. Now the equivalent resistance is different because the R3 and R4 are different. So we'll have 1,667 ohms. So if I now again use Ohm's law, the same current value with different resistor, I will have 0.621 microvolts RMS. So that's actually the second part for the second stage. Now we will look at the contribution due to the resistors. That's actually the final contribution. For that, of course, we use the white noise or the thermal noise formula for the resistors. So for that, of course, we look at the thermal RMS noise voltage in this general form given by this value, which is then 4 kT times the R, which is just the resistor seen at this node and also at that node, and times, of course, the noise bandwidth in the square of that, when that will give you directly your value in RMS value in volts. Okay. Now, if I now continue looking at the parameters, again, this is the Boltzmann's constant. We already discussed this. This is the temperature in kelvins, and we take for that the 300 kelvins, which is approximately 27 degrees. And R is the equivalent resistance in ohms seen at the node, and also this is the noise bandwidth of that part of the circuit. Okay, now for this, we have of course calculated already the equivalent resistance, which was 1,667 ohms, and our noise bandwidth, of course, was for this only was much larger, but since this is a complete circuit, it is then limited again by the first stage, which is then 554 kilohertz. So the noise bandwidth is then equal to the first stage, and the second stage must be done equal to each other because the first stage will limit the total noise bandwidth. Then we have the following expression again for the thermal noise voltage of the resistors. Again, substitute the values, we will get 3.91 microvolts RMS. This is a little bit smaller than the first stage because the resistors are also small. So if you have a small resistor, you will also have less thermal noise. Okay, we now have the necessary elements to calculate the input referred RMS noise voltage due to that the second stage at the input. So that is again calculated using the root sum of squares. This is the formula. We need, of course, these elements. We already calculated the first one due to that noise voltage source, which was 1.64 microvolts RMS. Now, due to that current source, which was calculated 0.621 microvolts, and due to the resistors, we just calculated 3.91 microvolts RMS. Now, take them together using this formula. You will have, of course, this expression, and that will give you, if you do the math, 4.29 microvolts RMS. Okay, that is for the input referred RMS noise voltage due to that second stage. And again, you see the largest value actually due to that resistors will dominate, because this is much closer than to that one. Okay, now we'll look at the total output referred RMS noise voltage due to that second stage only. For that, we need the closed loop noise gain of the second stage, which is, now for that we need again the closed loop noise gain of the second stage. That is then 6, and of course the input RMS noise voltage of the second stage, which is then already calculated 4.29 microvolts RMS. Then the formula for the output noise voltage due to that second stage only, that will be this expression. Now we have the 6 for our noise gain of the second stage. We have this value for the input referred RMS noise voltage, that will then 25.7 microvolts RMS, or in millivolts 0.0257 millivolts RMS. Now we have the necessary elements actually for each stage. Now we can calculate the total output referred RMS noise voltage. So that is now the next step. So the total output referred RMS noise voltage, that is then this expression. Now we have this value, or this formula. This is the contribution due to that first stage only, and this is the contribution due to that second stage only. And then we again use the root sum of squares formula to calculate the total output referred RMS noise voltage. Now, for the first stage, we have this value already calculated, and for the second stage, we have this value, just calculate that. Now, if you now substitute these two in here, you will have this expression, and that will be again very close to the largest one, which is then, in this case, exactly, due to the rounding off errors, 1.42 millivolts RMS. What you see is the first stage is definitely dominating the noise performance, so the second stage is not doing much in terms of noise. So, observations, again, the total output noise voltage of the circuit is almost determined by the noise contribution due to the first stage only. That is most of the case actually when you have a very high gain stage at the input. So notes is actually the following. If the first stage is a high gain compared to the subsequent stages, so you can of course have 3 or 4 stages, then the first stage will dominate the noise performance of the total circuit. Now that will give actually the following rule of thumb. Because the first stage or the input stage will dominate the noise performance of the complete circuit, of course, the engineers will often use a more expensive or more elaborate low noise amplifier for the first stage, and then less expensive amplifiers for the subsequent stages, because this first part will actually dominate the complete noise performance. That's actually, of course, if you look only in terms of noise. So that's actually our result. So we need, of course, verify this. But let's also look at the noise and the signal ratio, so the signal to noise ratio, SNR. So signal to noise ratio is a measure that compares the desired signal level to the noise level. This is actually briefly done, and in more defined form is then the ratio of the signal power to the noise power. Now, if I, of course, have a ratio which is larger than 1, higher than 1, which means in dBs, because it's expressed in dBs most of the time, greater than 0 dBs, that indicates you have more signal noise. And if you have, of course, less than 0 dB, which is a negative, then you have more noise than signal, which is, of course, not what we want. So that will be then the ratio between 0 and 1. Now, for the circuit, the SNR, the output for a specific frequency, can be calculated using this formula, which is the SNR is then equal to 20 log 1 over that total output referred RMS noise voltage. So you can already see this is already given in expression such that this is then again dBs. Now we have calculated what the total output referred RMS noise voltage was 1.42 millivolts RMS. So if I now substitute the values in here, I will have this. This then will result in 57 dBs. when we will verify this shortly in the simulations. So let's look at the simulation results. Frequency response, signal gain and the bandwidth. This is the plot. You can see the circuit with its own noise sources. And you can see the gain, DC gain actually, and you can see some labels. We'll discuss this shortly. The total signal gain is here 47.96, approximately that. And you can then calculate that, verify that by using the signal gain of the first stage and also the signal gain of the second stage. That was 50 for the first stage, of course in absolute sense, and also for the second stage was 5. So this is then 20 log, 250. That will give you also this value. So this dBs in the low frequency part is correct. So that's actually verified. The cutoff frequency was for the first stage was 353 kilohertz. That was actually our signal bandwidth. Again, our cutoff frequency, just looking at the first stage. And for the second stage, we had actually the 3 megahertz as our signal bandwidth. But if I look at this is the cutoff frequency of the complete circuit. It is 348 kilohertz. So it is a little bit less than what we have calculated, because the calculation was the cutoff frequency for this one was 353. And again, you can see this second stage, that frequency, the pole of that second stage has lowered actually the actual cutoff frequency and also the noise bandwidth and also then the noise voltage in the output. So you can see that shortly also in the later discussions. Now I've also labeled some extra points here, so you can see the gain at 100 megahertz. It is minus 31.6 dB approximately, and if you go then for example to 1 gigahertz, which is then 1 decade up, then the gain will drop to minus 71.6 dB. So you can see it is a decrease in 40 dBs for a decade increase in frequency. So the total signal gain decreases by 40 dB for a decade increase in frequency. But if you increase your frequency by 1 decade and you decrease by 40 dB, that means this part is already a second order system. So the slope is here minus 40 dB per decade. But for the second order system, that is the case. But for the first order system, it must be minus 20 dB. dBs per decade. So this part actually, after the second pole of this second stage, the circuit will behave as a second order system because the total system is actually a second order system. But for this part up to this part actually of this circuit, it is considered to be a first order system, and that's actually what we have used to calculate our noise at the output. Okay, this is then again seen here in the slope. So this slope will be then minus 40 dB per decade, and it is a second order system. Okay, let's also look at the input noise voltage spectral density. That's this plot. You can see the part here and also the part N, which is then of course growing for very large frequencies. And the minimum value is approximately 7.61 nanovolts RMS, root hertz I mean. Now the first part is actually this one, because this is a very large value. This part is not really visible, but this part is actually, again, the first part is the frequency dependent part, which is the 1 over F noise part. You have the frequency independent part, which is then this large region. And we have also a region which increases as a function of the frequency. That happens actually after 10 megahertz. So the input noise voltage spectral density will increase for these frequencies and larger. Now if I also look at the output noise voltage spectral density, this is then the plot. You can again see the 1 over F noise part, the broadband part, and you can see the last part which will go to 0 because the bandwidth limiting of the op amp. So that is what we have at the output. So at the input you don't see that, but in the output you can see it will be filtered out because the op amps will of course have its own bandwidth limitation. Now also a very important one is the total RMS output noise voltage. That's actually what we really need to check. Now we can see here that our calculation was 1.42 millivolts RMS, but I can see here in the simulation it is 1.341 millivolts RMS. So there is some difference here. So it is lower, and we already discussed something about this low noise due to that low noise bandwidth due to the pole of the second stage. So the second stage, the possible causes of lower output noise voltage can be the following. The first order approximation is not valid for the complete frequency response, which is of course true. It is not valid, but we have made an approximation. So there's some error, but it is lower. So how can we explain that this is lower, the simulation, than our calculations? Now, the noise from the first stage, this can be slightly reduced by the bandwidth limitation of the second stage. So because the pole of this first and the pole of the second stage will interact with each other, they will cause actually a pole splitting. That will cause then the actual signal bandwidth, or also the cutoff frequency, lower. We have seen that also in the body plot. It was 348 kilohertz and not 353 kilohertz. So the difference is of course just 5 kilohertz, but the noise bandwidth it will be of course also a little bit larger, that difference. So that can be explained by that pole splitting due to the two stages. So that's actually what we have, but how can we solve this problem? So how can we again look at a better estimation? So better estimation of the total output noise voltage can be given maybe just integrated actual close-up signal bandwidth and of the complete circuit, which is not an easy task. I won't do that here. But I will use this as a first approximation. I will use an evenly weighted average of the noise bandwidth conversion factors. So I will call this the K sub n average. Now we know for the first stage it was of course just first order. I can just assume it is then pi over 2. But I have also a second order part of the system. Then for that the K sub n, which is then the noise bandwidth conversion factor, is 1.222. Okay, I will now take these two and calculate the average of that one. Just very straightforward simplification, but it is maybe a better estimation to look at the complete frequency range. So that will again give me 1.396 instead of just pi over 2. Now, if I now recalculate this using this conversion factor and then calculate the closed loop noise bandwidth. So this is of course the single bandwidth we have of course we will use for our first for our complete circuit, because the first stage will dominate this. Then I have the noise bandwidth, new one, using this average value times the signal bandwidth due to that first stage. That will give me now a little bit lower noise bandwidth, which is then 493 kilohertz instead of 544 kilohertz. So it is lower. So using this as our new closed-up bandwidth, we get these results. Okay, these are just of course the descriptions. What you see that for the first stage you will have 1.544 microvolts RMS, again exact same for the first stage. This is just due to the input noise voltage due to that op-amp noise voltage source. And this is the input noise voltage due to op-amp's noise current source. You can see the values here. And also due to the resistors and also the input noise voltage. So actually combining these three, and also for the second stage combining these three. And this is the output noise voltage due to the first stage, and this is the output noise voltage due to the second stage. Now if I now look at these two values and then using this formula again, I can now calculate this and come actually to this value. And this is now the recalculated value using this estimation. So it is 1.336 millivolts RMS. Now what was our calculation in the, or what was our result in the simulation? So in the simulation it was 1.341 millivolts, and this is of course a very closer value, much closer than the first one, which was 1.42 millivolts. So this estimation by averaging actually the noise bandwidth conversion factors is a nice result, and it will be of course used if you have a situation where you have a very large or not close value in your calculation with your simulations. Okay, let's also look at the total RMS noise voltage again. This is then the results, again using the recalculation value. This is of course calculated here, and this is the simulation result, and this is what we have done. And now we have these two, and you can see it is very close to each other. Okay, now let's look at the final one as the signal to noise ratio. Signal to noise ratio for this circuit, again, it starts very high at very low frequencies and then goes down and then approaches actually a constant value of 57.5 approximately dBs. Now our calculation using this formula, using this value was this, so it was 57 I mean dBs. Of course, in actual output referred RMS noise voltage was a little bit lower, so we will have actually also a little bit larger SNR because it is inversely related. So you can also see the simulation is also a little bit larger, so that also confirms that the value here for the output referred RMS noise voltage must be a little bit smaller, such that the SNR is larger, but it is very close. So again, confirmation of the calculations using the simulations. Alright, this was for our example using a two-stage amplifier. You can see there are several steps to be taken. You need to consider actually each stage separately and then add them up using, of course, again the root sum of squares because we are working with noise powers. And then we have verified this in our SPICE simulations what the result was, and I also seen that the result in the simulation for the output referred RMS noise voltage was first 1.42 milliwatts RMS, and we have then estimated, made a better estimation by using the average value of the noise bandwidth conversion factors, and that resulted in a much closer value with the simulation and also the calculations. Alright, thanks again for your attention. This was our nice example, I think, about a very broad subject of noise and now in two-stage amplifier format. If you have any questions about this, please let me know and I will try to answer them as soon as possible. Thanks again and see you next time.